In this video, we're going to discuss the basic ideas that lie behind the integral test for series. Recall that by definition, a series will converge if the sequence of partial sums for that series also converges as a sequence. In that case, the sum of the series is equal to the limit of the sequence of partial sums. Also by definition, we say that a series diverges if the sequence of partial sums diverges as a sequence. This means that to use the definition to show that a given series converges or diverges, we would need to have a formula for the partial sums, S sub k, and then be able to compute the limit of that sequence. This is really only possible for two main classes of series, namely telescoping series, where the partial sums can be computed and collapsed to allow the limit to be computed, and for geometric series, where we're able to easily derive a formula for the partial sum for which the limit can be taken. For all other series, finding a formula for the partial sums can be extremely difficult or even impossible. Therefore, our new goal is to establish a variety of tests that can be used to determine whether a given series converges or diverges. This will allow us to determine whether a series converges or diverges without having to find a formula for the sequence of partial sums for that series and then find the limit of that sequence of partial sums. Using the various tests that we're going to establish will be much easier than dealing with partial sums for series. However, there is a trade-off. Typically, when we use one of these tests to determine whether a series converges or diverges, we will not be able to actually determine the sum of a convergent series. If we actually need to know more information than just that the series converges, we would then have to find partial sums and take the limit of those partial sums in order to find the sum of that series. We've already seen one simple example of such a test, namely the divergence test, which says that if the limit of the terms of our series is non-zero, then the series must diverge. This gives us a way to check for the divergence of a series, namely by computing the limit of the terms of the series, without having to deal with partial sums in any way. We now turn our attention to another test, known as the integral test, which uses improper integrals as tools to help determine if certain series converge or diverge. In order to understand the idea behind the integral test, let's consider two series, the series from n equal 1 to infinity of 1 over n, and the series from n equal 1 to infinity of 1 over n squared. Let's think of these series in sort of an outside-the-box way, and let's think about them geometrically. Specifically, let's think about the graphs of the functions that correspond to these two particular series, namely the functions f of x equals 1 over x and f of x equals 1 over x squared along the interval from 1 to infinity. Let's build rectangles under the graphs of these two functions along the interval from 1 to infinity, with the rectangles based on the x-axis and having a width of 1. We're going to start building these rectangles at x equal 1 and moving to the right indefinitely. We're then going to look for a connection between the area of these rectangles and the sum of our series. We'll start with the series n equal 1 to infinity of 1 over n, and we'll first write out the first several summands of this series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. We're now going to consider the graph of the function f of x equals 1 over x and build rectangles based on the x-axis from 1 to infinity using the curve. The height of each rectangle will be the function value at the left endpoint. So, for example, the rectangle based on the x-axis between 1 and 2 will have a height of f of 1, which is equal to 1. And the rectangle based on the x-axis between 2 and 3 will have a height of f of 2, which is 1/2. We can see here 5 such rectangles that have been produced. We can also see that the area of each rectangle is actually just going to be the height of the rectangle, since in order to find the area, we would multiply the height of our rectangle by the base width, which is 1. And so these 5 rectangles have an area of 1, 1/2, 1/3, 1/4, and 1/5 respectively. We notice that these are the first 5 terms of our series 1 over n. If we continue to build rectangles indefinitely going in the positive x direction, the area of each subsequent rectangle will be the next summand in our series. This observation demonstrates that the sum from n equal 1 to infinity of 1 over n, the series that we're considering, is going to equal the sum of all of the rectangle areas along the interval from 0 to infinity. This gives us a geometric way of representing our given series as the areas of an infinite number of rectangles. What we notice then is that this sum of all of these areas will be larger than the area under the curve along this interval from 1 to infinity. We can see this by noticing that all of the area under the curve will be contained in these rectangles, but that there's also area above the curve that will be counted by the rectangles. So for example, these regions that are being shaded in green are all considered area of rectangles here, but the area is not under the curve. And so these green shaded regions would be counted by our series, but would not be part of the area under the curve, which we know is given by the improper integral from 1 to infinity of 1 over x dx. And so here we've related our original series, n equal 1 to infinity of 1 over n, to the improper integral 1 to infinity of 1 over x dx. The improper integral from 1 to infinity of 1 over x dx is easily computed. We know that this is going to be the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. We can evaluate this integral by finding an antiderivative for 1 over x, which would be the natural log of the absolute value of x. And we'll evaluate that from 1 to b by the fundamental theorem of calculus. When we do that, we're going to get the natural log of absolute value of b minus the absolute value of 1. We want to take the limit of this difference. Of course, natural log of 1 is equal to 0, so we really just want the limit as b approaches infinity of the natural log of b, and this diverges to infinity. The larger b becomes, the larger natural log of b will become, and so this improper integral is divergent. So now we recall that using the area of the rectangles, we notice that the sum from n equal 1 to infinity of 1 over n was going to be greater than the improper integral from 1 to infinity of 1 over x dx, and the calculation above shows that this integral is a divergent integral and is equal to infinity. And in this case, the series, the value of our series, must be greater than an infinite value, and therefore we can conclude that our particular series that we started with, the series 1 over n, must diverge. There's no way for this series to equal a finite number, since it needs to be bigger than some quantity, namely this improper integral, which has an infinite value, and therefore our series must diverge. Notice we were able to reach this conclusion without considering partial sums in any way. We simply related our series to a corresponding improper integral and used the improper integral calculation above to make our conclusion about our series. We can now do a similar analysis with the series from n equal 1 to infinity of 1 over n squared. To handle the series from n equal 1 to infinity of 1 over n squared, we're going to consider the graph of the function f of x equals 1 over x squared. We're going to build rectangles based on the x-axis starting at 0 and going on to infinity of width 1, and the height of each of the rectangles is going to be the function value at the right endpoint. By doing this, we see that the area of our rectangles will be 1, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, etc. And these are the terms of our series with term 1 over n squared. Like in the previous example, we can then relate our series, n equal 1 to infinity of 1 over n squared, to the improper integral by thinking of the series as the sum of all of the rectangle areas shown here. The one problem with this is that when we do eventually use the improper integral from 1 to infinity, it's only going to consider what happens starting with x equal to 1. In particular, the improper integral will not take into account this first rectangle of area 1. So what we can do is think of the sum of all of the rectangle's areas as 1 plus the sum of the rest of the rectangle's areas. And so by the rest of the rectangles, we mean all of them except the first one with area 1. Now by looking at the graph, we see that 1 plus the sum of the remaining rectangle areas will be less than 1 plus the area under the curve, because the rectangles here all lie under the curve, and there is additional area under the curve that's not inside the rectangles. This calculation, 1 plus the area under the curve, is then equal to 1 plus the improper integral from 1 to infinity of 1 over x squared dx. So now we can use this improper integral from 1 to infinity of 1 over x squared dx to relate back to our series of the form 1 over n squared. So the improper integral from 1 to infinity of 1 over x squared dx, we can compute this by thinking of it as the limit as b goes to infinity of 1 over b of 1 over x squared dx. We can find an antiderivative of our integrand here. So the antiderivative of 1 over x squared will be negative 1 over x, and we'll evaluate that from 1 to b. When we do that, we get the limit as b goes to infinity of negative 1 over b plus 1. And as b goes to infinity, negative 1 over b will go to 0, and we get a value of 1 for this particular improper integral. So this improper integral converges. We can now relate our original series, n equal 1 to infinity of 1 over n squared, to this improper integral. We previously saw that this sum is going to be less than 1 plus the improper integral from 1 to infinity of 1 over x squared dx. And we just showed that this improper integral is convergent and is equal to 1. And so this shows that our summation from n equal 1 to infinity of 1 over n squared is less than 2. It should also be obvious that this sum is greater than 0. We're adding together a bunch of positive numbers, and the result of that should certainly be positive. Geometrically, this series is giving us the sum of areas of rectangles, and this would always be a positive number. So what we see here by this string of inequalities is that the sum of our series must be somewhere between 0 and 2, and therefore our series must converge. It's impossible for this particular series to have an infinite value because the series sum has to be between 0 and 2, and everything between 0 and 2 will be a finite number, and therefore we have a series which converges to whatever number that happens to be. And so here we have, again, an example where we know the series converges without considering the partial sums in any way. We've now considered the two series that we aimed to consider, the series of 1 over n and 1 over n squared. In both cases, we were able to associate to the series an improper integral of the corresponding function, the integral from 1 to infinity of 1 over x, or 1 over x squared, respectively. And in both cases, what we've observed is that the series and the improper integral had the same behavior. For the series n equal 1 to infinity of 1 over n, we saw that the series and the improper integral from 1 to infinity of 1 over x dx both diverged. And in this last example, we saw that the sum from n equal 1 to infinity of 1 over n squared and the improper integral 1 to infinity of 1 over x squared dx both converged. What the integral test will ultimately tell us is that under certain conditions, the series that we have and the associated improper integral will have the exact same behavior. Either both will converge or both will diverge. This is a really helpful tool because we already know how to compute improper integrals and determine whether they converge or diverge. And so knowing this, we'll be able to determine the convergence or divergence of our series without having to deal with partial sums or without having to use the graph and look at rectangles. We can simply jump straight to the improper integral and compute it, determining whether it converges or diverges. Here's a formal statement for the integral test that was suggested by the previous examples. We're going to be given a series from n equal 1 to infinity of a sub n, and we want to let f be the associated function to that series term. In other words, we want to define f so that f of n is equal to the nth term of our series a sub n for all values of n. The integral test says that under these three bulleted conditions, that f is positive, continuous, and decreasing on the interval from 1 to infinity, then the series n equal 1 to infinity of a sub n and the improper integral from 1 to infinity of f of x dx will have the exact same behavior. Either both of those series and integral will converge, or both of them will diverge. As stated previously, if the associated function to our series has an improper integral that can be easily computed, this test is very nice because we can determine whether the series converges or diverges by simply computing an improper integral. Notice that the three conditions for f are incredibly important. F needs to be positive, continuous, and decreasing for this test to apply. While most functions we'll see will have these properties, it's worth noting that there are cases where one or more of these properties will not hold. And in those cases, this test does not apply and could be used to reach a false conclusion. It's also worth noting that the integral test can be applied to any series, not necessarily those starting at n equal to 1. So suppose we had a series at the very beginning that started at n equal to 2. Then everything here remains completely valid as long as we adjust everything to starting at x equal to 2. So for example, we want our function f to be positive, continuous, and decreasing on the interval from 2 to infinity. And then we would say the series from n equal 2 to infinity of a sub n and the improper integral from 2 to infinity of f of x dx would both converge or diverge. Of course, 2 is just another example of a starting point here. We could have a series that starts at n equal to 5, in which case we would look at the interval from 5 to infinity and then make a conclusion about the series from n equal 5 to infinity using the improper integral from 5 to infinity.